Two of the triumphs of the early 20th century were the development of Einstein's theory of relativity and the theory of quantum mechanics. Einstein's theory came in two categories. One was his special theory of relativity, which mostly dealt with objects traveling at constant velocity, and the second was his theory of general relativity, with objects whose velocity is changing. And yes, for the purist, that delineation is not perfect, but it works pretty well. If you take his second formulation and follow it down the rabbit hole, you go from changing velocities to accelerations and eventually gravity. Ultimately, Einstein's theory of general relativity is a sophisticated theory of gravity, which has taught us that what we experience as gravity is really the bending of space and time. Pretty weird stuff, to be sure, but it's been proven time and again with detailed predictions about the orbit of Mercury and the recent observation of gravitational waves. There's no credible doubt in the scientific community about general relativity. It's a good representation of reality. The problem comes when Einstein's ideas meet quantum mechanics. Now, there's no issue with special relativity. Special relativity and quantum mechanics merge just fine. The result is quantum electrodynamics, quantum chromodynamics, and quantum field theories in general. I made perhaps a dozen videos on those subjects. However, when general relativity, which is to say Einstein's theory of gravity, meets quantum mechanics, the result is very different. The two theories simply can't coexist. You get infinities and conceptual difficulties everywhere. And even though some of the very smartest minds of the last century have worked on this, it's still a problem. We don't know how to merge quantum mechanics and gravity. Now, I made an earlier video about just why scientists think that a quantum theory of gravity should exist, and it's probably worth your time to take a look at it. But in this video, I'm not going to repeat those reasons. Instead, I'm going to just talk about an idea as how one might merge quantum mechanics and gravity. The name of this particular idea is called loop quantum gravity, or LQG. Essentially, what it does is try to use what mathematicians call discrete mathematics. An example is simple counting, and it is this type of math on which quantum mechanics is based. This approach could avoid all the nasty and troubling infinities that have perplexed mathematicians. Loop quantum gravity then imposed two core principles of general relativity. The first is what is called background independence. This means that it doesn't require that space exists prior to writing down the theory. To give an analogy, if you're writing on a piece of paper, you can assume the paper is there, and then you write on it. Further, you can assume the paper has a certain shape. It's flat. The assumption of flat and unchanging space is very common for most physics theories. But in loop quantum gravity, you make no assumptions on the nature of space. To continue our metaphor, it's as if the equations can exist independently of the paper, and even more interesting, they can bend and change just like general relativity. The second core principle has the very cool name of diffeomorphism invariance. The phrase is definitely a winner that you can drop at your next cocktail party. Diffeomorphism invariance simply means that what's going on at a point in space depends only on that point and not where it's located in space, nor what's happening at other points in space. So, if you combine those two core ideas and don't require that the mathematics be continuous, you can then explore the equations to find out if they force you to conclude that space and time is continuous or quantized, and it turns out that, a drum roll please, both space and time are quantized. One of the core consequences of that conclusion is that loop quantum gravity implies that there is a smallest length, which is 10 to the minus 35 meters, a smallest area, which is 10 to the minus 70 square meters, and a smallest volume, which is 10 to the minus 105 cubic meters. Further, there's a smallest time, which is 10 to the minus 43 seconds. So that's a very strong implication. It says that it's literally impossible to have a smaller volume than 10 to the minus 105 cubic meters. It's kind of like looking at a beach closer and closer until you're resolving individual grains of sand. But in loop quantum gravity, it's impossible to go smaller than a grain of sand, which is our metaphor for a grain of space. Similarly, this implies that there's no shorter duration than a quantum of time. It's like a digital stopwatch which counts out the seconds, one after the other, but there's nothing in between, except this time, which goes 10 to the minus 43 seconds, then 2 times 10 to the minus 43 seconds, 3 times 10 to the minus 43 seconds, and so on. That's really the core consequence of loop quantum gravity, the smallest bit of space and time. Now, there's been a bunch of mathematics written down about this and ways to draw this out involving terms like spin networks and spin foam, but those take some time to dig into and they don't really help your understanding all that much. So I won't go into them here. I'll put a link in the description if you want to read more. Now, one of the interesting questions is how do you get from the quantum of space and time to Einstein's theory of general relativity? It's because when you add mass and energy, you can distort the shape of the little volumes. Now that seems like it wouldn't make sense because I said there were quanta of lengths, areas, and volumes. But you need to remember that you're bending space and time, and that has a property that you can distort the local definition of space in such a way that the volumes are unchanged. So these ideas of quantum space-time are good and all, but are they real? I mean, is there any way that we can test them? Well, we can't get at them with our current particle accelerators. They simply aren't powerful enough. But it turns out that there's at least one way to test the theory. It turns out that if you take the idea of quantized space and time and apply it to the passage of light, there's hope. Loop quantum gravity implies that different colors of light travel through space-time at slightly different speeds. High-energy light, that is to say shorter wavelength light, travels more quickly through quantized space-time than longer wavelength light. Now the differences are ginormously small and aren't accessible except through a cute idea. If you let light travel for a very long distance across the known universe, maybe you'd see a difference. There are a few examples of sources of light that are bright enough to be seen across the visible universe, and one of them is called a gamma ray burst, which are the brightest explosions in the history of the universe, second only to the Big Bang itself. They allow us to look at different color light that has traveled for a very long time. There are multiple instruments looking for these, but one of the most powerful is called the Fermi Large Area Telescope. By the way, even though the Fermi telescope and my own Fermilab share a name, they aren't related in any way except for respect for Enrico Fermi. When astronomers looked at the distant gamma ray burst and analyzed the arrival time of light of different wavelengths, it appears that light of all wavelengths travel at exactly the same speed. So this could be a problem for loop quantum gravity, or it could just mean that this particular prediction isn't universal. We just don't know. But we'll keep working on it because either way, the idea of a smallest bit of space and time is simply a very cool idea. Okay, that was fun. Do I believe in loop quantum gravity? No, of course not. There's no confirming data. But it's a fascinating idea and I'm very interested in finding ways to test it. If loop quantum gravity is real, I'm sure we'll figure it out. And even if it's not, the journey will be fascinating. Learning about this stuff is a great way to stretch your mind because, of course, physics is everything.